So let's take that basic idea of travel graphs and extend it. So applications of calculus in our physical world. So there was the idea of displacement. In maths we usually use x to be displacement. It doesn't have to be x. In fact, when we start talking about projectile motion, we'll also use y to distinguish vertical movement and horizontal movement. I think in physics they use s, don't they, for displacement? But it's distance from a point but with some direction. So plus or minus tells us in which direction. Velocity, v, obviously. But now we know also that it's the rate of change. We could write dx to t. It's the first derivative of displacement with respect to time. Now, the dot notation for the derivative is purely used in these motion questions. So x dot means velocity. Doesn't actually mean the first derivative, although it is the same thing, if you get what I mean. We usually use it when we talk about velocity equations. So rate of change of displacement with respect to time, in other words, it's speed, but with direction. And then we have acceleration, which now we could write it as a, but it's the rate of change of velocity with respect to time, so we could write it as dv to t. We could write it as the second derivative of displacement with respect to time, and using the dot notation then it could be x with 2 dots, or velocity with 1 dot. So rate of change of velocity with respect to time. And the horrible thing about acceleration is we don't have a different word for the vector and the scalar. They're both called acceleration. So whilst we can say with velocity as the vector and speed as the scalar, with acceleration is the vector and acceleration is the scalar. So it's sort of weird. But an important thing to point out is deceleration. This fictitious thing called deceleration. There is no such thing as deceleration. Okay, as far as we're concerned. Slowing down is simply when acceleration is in the opposite direction to which you are travelling. So you still have an acceleration, it's just that the direction is opposite to the direction that you're travelling. Hence you will slow down. Alright, so here is a displacement time graph. But because I'm talking about displacement time graph, unlike our travel graphs, I can have negative values. So it goes down -1, -2. But still the same ideas. The slope at any particular point would give me the instantaneous velocity. If I wanted to draw the velocity graph, then I'll just plot it underneath. Key things I know, well, I know stationary points is when the derivative is 0, so they will become, well, t-intercepts in my graph. I know when it's increasing it's going to be positive, when it's decreasing it's going to be negative. In fact, I'll end up with something like that. And this time the slope would give me the instantaneous acceleration. And then if I wanted to draw an acceleration graph, again I can use the same ideas and we'll end up with, in this one, a straight line. And given how I drew my displacement graph, it kind of makes sense because it sort of looks like a cubic. Differentiate a cubic, you get a quadratic. Differentiate a quadratic, you get a linear function. So, those standard questions that we saw with travel graphs. What is the distance travelled? Well, it's 7 metres. I could just look at my graph and read off, but they're saying distance. As opposed to the total displacement, how far is it from its starting point? Well, it's -1. It's 1 metre in the negative direction. Average speed, distance, 7 over time. Average velocity, displacement over time. But we don't need the graphs now. If we've got an equation for the motion, we can just use the equation. So we've been given the displacement formula here, x equals t cubed minus 21t squared. We want to come up with an expression for acceleration. So that's the second derivative. So differentiate it once, I get a velocity equation. Differentiate it twice, I get an acceleration equation. So when is the particle stationary? So again, same sort of questions, I now just don't have the graph. When is it stationary? Kind of a good word when you think about it. Because it's stationary when the velocity is 0. But velocity is the first derivative, and the first derivative is equal to 0 at stationary points. Sort of neat how that ties in. When you are writing down your solutions, don't just go and say, oh, I'm going to solve v equals 0. Explain yourself. Why am I doing that? Well, I know the particle is going to be stationary when velocity is 0, so I'll go and solve that equation. And we get t equals 0 and 14. How you write your answers up to you. I've made it look fancy, I suppose, by using the word initially. So particle is stationary initially, but then again after 14 seconds. All right, so what we got here? This time they've given us an acceleration equation. And we have to find out where it is after 3 seconds. Okay. So acceleration, now I'm going back the other way. So to get a velocity equation, I'm going to have to integrate. So I get 2t plus 3t squared plus a constant. We want to eventually find the position. So I'm going to have to integrate again. But before I do that, let's go find the value of the constant. There must be some information there that'll help us. What do we got? T equals 0. Starts from rest. So t equals 0, velocity equals 0. So the constant does turn out to be 0. So had you forgotten to go plus a constant in this case, you would have got lucky because the constant's 0. V is 2t plus 3t squared. All right, let's go integrate that one. T squared plus t cubed plus constant. It's okay that I've used c again because they're totally different equations. If I had them in the same equation, then yes, I'd want to use a different value than c because it's not necessarily going to be the same constant as the other one. Sub in our values we know, t equals 0, x is 7. So in this case, had you forgotten the constant, you'd be in trouble because we've got the constant is 7. So there's our equation. We want to find the position. So when t equals 3, sub in, it's 43. Constants are a hassle, my opinion, so I don't worry about them. I just do everything as definite integrals rather than indefinite integrals. Right? dv to t, remember that's what acceleration is. dv to t is that. What I do is this technique called separating the variables, and we'll see that in differential equations. We'll look at this a bit more in detail. So I put all the things that have v together and all the things that have t together, but then I also integrate both sides. But I make it a definite integral. And so the limits match up. So they tell me when t equals 0, v equals 0. So I've got the zeros on the bottom of the integral sign. At the top, I'm trying to find a link between t and v. So if I solve this, I should get our answer. So left-hand side, I can pretty much go straight to v because it's just integral of dv. So that's just going to be v. And sub in v, you get v. Minus sub in 0, you get 0. So that's sort of simple one when it's just going 0 to v of dv. I can go straight to v. Right-hand side's a little bit more involved. But we end up with 2t plus 3t squared. Okay, that's velocity, which is, of course, dx to t. Again, let's separate. Now, we were told t equals 0, x equals 7. We want to know what is x when t equals 3. So there's the equation I need to solve to find x. You'll notice now on the left-hand side, because it wasn't as simple as going from 0 to x, I've actually put the limits in there, 7 of x. And right-hand side, we're going 0 to 3, sub in 43. So I don't have to worry about making the mistake of forgetting about the constant or anything like that. I can, bang, go straight to it. That's personally how I prefer to do them anyway. All right, HSC one. Oh, that's an interesting function. What's the displacement when t equals 0? So it starts off quite a simple little question. We just got to sub in t equals 0. We get -1. Show that. Remember, this is coming from a tune-up paper, by the way. So they're being very generous here. Show that x equals 1 minus 4 on t plus 2. Oh, okay. Well, x is t minus 2. So there we go. Combine it all into one fraction, and what do you know? I get t minus 2 on t plus 2. But then, hence find expressions for velocity and acceleration. So I guess what they were doing is giving everyone a real big hint. Don't go and differentiate this t minus 2 on t plus 2, because this x equals 1 minus 4 on t plus 2 is going to be a heck of a lot easier to differentiate, because the 1, of course, becomes 0. We have a constant on the top of that, so it's minus the derivative on the function squared. And there we go, 4 on t plus 2 squared. And once again, to get acceleration, we've got a constant on top, so I can do that again. Minus the derivative on the function squared. And that tidies up to be -8 on t plus 2 cubed. Is the particle ever at rest? Give reasons. Well, velocity is 4 on t plus 2 squared. Well, that can't equal 0. Constant on the top of the fraction. There's no way I'm getting 0. So no, it's never at rest. In hindsight, is that good enough reasoning? Maybe I should have explained why it can't equal 0. What is the limiting velocity? So as time is approaching infinity, what's happening to this particle? So the limit as t approaches infinity of velocity, Remember, that was 4 on t plus 2 squared. That's 0. Of course, you could have used the graph. There's our graph, and we can see as t increases, yep, that graph goes towards 0. So either way, there's our limiting velocity. Let's have a look at another one. X this time is a trig graph. I just think this was a fancy way of getting them to draw a trig curve. Because it says, sketch the graph of X, but we made it look like, oh, look, it's velocity time or displacement time. Really, it's just a trig graph we're drawing. So amplitude is 1. We've shifted the whole thing up 3. The period will be pi. So I'm going to mark off my divisions every pi on 4. So there's my axes. I'll just draw in the axis of our function, because remember it's been shifted up 3, so I know where to plot the points. It's a sine graph, so I would start at the axis, and then it will go up and down, up and down, up and down. So there's our graph. Using your graph or otherwise, don't go otherwise. Find the times when it's at rest. It's so much easier to use the graph. Because when is it at rest? Well, it's going to be at stationary points. So I just got to name all of those stationary points. So starts off, t equals pi on 4, then 3 pi on 4, then 5 pi on 4. So much quicker than going and doing the actual calculus and locating those spots. Describe the motion. Oh no, we have to use words. I used a big word. Oscillate. The particle oscillates between 2 and 4. Alrighty. 9b.